This place value chart is going to help you understand the place values of decimals. A decimal number has two parts, whole number part and decimal part. In the whole number part, we started from ones, tens, hundreds and so on. And the decimal part is started from tenth, which represents 1 upon 10 or 0.1, hundreds, which represents 1 upon 100 or 0.01, then thousands, which represents 1 upon 1000 or 0.001, and so on. And the point here is called decimal point. This point separates the whole number part and decimal part. Using these steps, you can move the numbers up and down and adjust them as you want. For example, let's take the 6th number as 100 in 100 place, and the 10th one, let's take 4. Now the number is 642.235. In the decimal part, we do not say the number as written in its value. We say the number as its face value. For example, the face value of 2 is 2, so we will also say 2, not say 20. 2.10 is also said but in the expanded form. So it will be said 235. The number is 642.235. So these are the place values of decimals.
So first we'll fold our circle into two equal halves. We'll fold it again. And fold one more time. Now we will open. We will find that our circle has been divided into 8 equal parts. Now we will cut each part of our circle. Like this. Cut down all of the 8 parts. Now I will arrange all of these 8 parts in such a manner where they look like a parallelogram. As I have cut this shape into 2 equal parts, we will do the same in our rest of the parts. Cut out to form a rectangle. So as here we can see, the area of rectangle is equal to our area of circle. So area of rectangle is equal to area of circle. Area of rectangle is length into breadth, which is equal to area of circle. So the length of this rectangle is equal to the half of the circumference. So 2 into pi into r into breadth. And the breadth of a rectangle is the radius. So into r is equal to area of the circle. 2 and 2 cancels and the remaining is pi r square. So therefore we have proved that why the formula of area of circle is pi r square.
This is an activity related to the areas of two triangles with the same height and different bases. So here we will be constructing two different triangles. The height of the both will remain as 7 units and the base of one 4 units and of the other 5 units. So this is how we created two different triangles, one A, B, C with base 4 units and height 7 units, and another of A, B, D with base 5 units and height 7 units. Now therefore, as we know the area of the triangle is half base into height, the area of the triangle ABC is 28 by 2 units square, whereas the area of the triangle ABD is 35 by 2 units square. Now, the ratio of their areas is 4:5 and the ratio of their bases is also 4:5. Therefore, hence it is concluded that the ratios of the areas of two triangles with same heights but different bases is equal to the ratios of their bases. This is an activity which demonstrates the very important properties of two triangles between the same parallel lines. So this is an already constructed triangle between the two parallel lines L and M with this as a base. Now we will be constructing another triangle with the same base between the same parallel lines but at a different point. So this is the orange one is now a new triangle. And if we calculate the areas of both of these triangles comes out to be equal because we know that area of a triangle is half base into height, and as these two have the same bases and the same height, that is between the two parallel lines, therefore the area will remain same.
Friends, you all would be knowing about kacha houses and pakka houses. How are these houses made up of? Well, maths is applied in everything around us. Here is one of the examples. On my right, you can see these two houses which you would have seen in villages. These are called kacha houses. These houses are made by the combination of 3D shapes. The first house is made by the combination of cube and a cone, while the other one is made by the combination of cylindrical and cone shape. So in our villages and small towns, we are using mathematics to construct houses. Coming to a Pakka house, I have shown you a building which you would have seen in cities. These buildings are also made using mathematics. For example, here the building is cuboidal in shape.
So what is pi?
Pi is the ratio of the circumference to diameter of the circle.
Anushka, you know, pi is an irrational number, which means it is non-terminating and non-real.
But wait, how can we calculate the value of pi?
Just by dividing the circumference by the diameter. It's that easy.
I don't believe this. Can you show me with an example?
Yes, we would all see this with the help of a practical. Here we have with us our two circles and a string. We would be showing that pi is the ratio of the circumference to the diameter of the circle, which is approximately equal to 3.14. So for that, with this string, we would measuring the length of the circumference of the small circle. Now, after measuring this length of the circumference, we would measure it with the help of a scale. By checking on the scale, the length of the string is approximately equal to 47.1 centimeter. Now, we would be measuring the length of the diameter of the small circle. The diameter of the circle is approximately equal to 15 centimeter. Now, we would divide this circumference with the diameter of the circle. Now, taking in calculator, we put the values, that is 47.1 and 15 centimeter. On dividing, we would see that we got an approximate value of 3.14, and it is true for all these circles.
First, take any paper that you can get at home and take another paper and cut it with a radius of 5 centimeter. You can take any radius, it's your wish, but cut the paper well. Now get a glue and apply it thoroughly on the circle and paste it on the paper that we had before. Now using a ruler, draw lines on both sides. As you can see, the first line is drawn. Draw the other line, and here we have it. Using your hands, fold the paper just like this and unfold it again, and using a ruler, measure the both sides, and in conclusion we notice that the lines when measured are equal, which proves the fact that the external tangents drawn around a circle are always equal.
Okay, so I will now tell the IXI method and why is it called IXI. So now the IXI method is called because of its sequence, which is actually the IXI method. Okay, so now let's take an example like 47 multiplied by 70, or maybe it be 8. We can now find. Okay, so let us assume that this is AB, we are multiplying AB multiplied by CD. Okay, so A is 4, B 7. You get the idea, okay? So now I will tell you the steps involved in the procedure. There are 3 steps involved. Okay, so the first step is actually B multiplied by D. Okay, so now multiply B into D. So the B is there, 8 multiplied by 7, which is equal to 56. So now we will write the 1's digit here and the other digit, the 10th digit, in the carry column. Okay, don't forget the carry column. So the second step involved is a bit more complex, and the most complex in the procedure is AD. We multiply A into D, and we multiply B into C, and we add those both. So it is actually, the formula is AD plus CB. So here it is 7 sevens are 49 plus 8 multiplied by 4 is 32, and add these up, it's 81, and don't forget to add this, goes to 86. Add the 6 from here to here, and add this to the carry column. Now let's try the third and the last procedure is multiply this. So this A multiplied by C, and so it is 4 into 7. So 7 4 is 28. Okay, and add this up. It is 34. It's 36 actually. Okay, so the answer is 3666.
Starting with the basics, here are the 3 axes: the x-axis, the y-axis, and the z-axis. Point to be noted is that all of these three axes are mutually perpendicular to each other, which means it forms a 90-degree angle between any of the two axes. Going deeply, any point lying on any of these axes will only have one dimension, which means it will have a value either in x-axis or in z-axis or in y-axis. The other two values will always be 0. Next comes our 2D figure, which is the plane commonly known as the Cartesian plane, consisting of length as well as breadth. These planes are formed with the help of any of the two axes, like this xy plane is formed using x-axis and y-axis. The yz plane is formed with the help of y-axis and the z-axis. Similarly, the zx plane is formed using the x-axis and the z-axis. Point lying on any of these planes will have the value of the third coordinate as 0. For example, any point lying on xy plane can have the coordinate as x, y, 0. After this, when taking this concept into a 3-dimension, we can see all of these 3 planes cut the region in 8 equal octants. The first 4 cubes, which represent the first 4 octants, are represented here. Here, the cube comprises of length, breadth as well as height, which means it requires all the 3 axes, the x-axis, the y-axis and the z-axis to be formed. The cubes for the downward octants are shown in this figure. As we can see that these cubes are present in 5th, 6th, 7th and 8th octant. This image represents the octants coordinates table. Here is the figure which shows all the 3 planes. The table depicted here describes about the sign convention of the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th and 8th.
I'm going to tell you the difference between volume of cone and cylinder when same radius and same height. Here I have taken a cylindrical glass of radius 3 cm and height 7 cm. Same here with the cone. The formula for cylinder is pi r square h and the formula of cone is 1/3 of pi r square h. Firstly, I'm going to show you the practical. Here, when I take one full cone and pour it into this cylinder, second full cone, lastly the third full cone. So here now you can see the cylinder is full. Now you can see that when I take 3 full cones full of water, this cylinder becomes full.
We are here to give an explanation on how integral calculus proves to be useful in finding areas under curves. Now we have a curve, we require the knowledge of calculus, particularly integral calculus. This is a part of parabolic curve whose equation is y square equal to x. Now we bound the area under this curve by dropping perpendiculars on the x-axis. Let us consider a very thin rectangular strip whose length is y and breadth is dx. The area of this elementary strip will be y dx. In order to find out required area, we need to integrate all the strips that contribute to the area under this curve. Thus, the required area is integration y dx. In prospect of x-axis, this curve spreads from 1 to 4, which are mathematically known as limits. A proper equation that we get is integration y dx limit 1 to 4. Finding value of y from the equation of curve, we get y equal to under root x, which is equal to x to the power half. Putting values in above equation, we get integration x to the power 1 by 2 dx limits 1 to 4, which can further be solved and we get the answer as 14 by 3 square unit. Now for the explanation part. And we get the answer as 14 by 3 square units.
Using integral calculus, we can even find areas of more complicated graphs. Like here, the area to be calculated is bound by a parabolic curve and multiple lines. Here we have a parabolic curves part whose equation is y equals to x square plus 2. We also have a line of equation x equals to y, and finally we have another line of equation x equals to 3. In order to find the area of the bound region, we need to calculate the area under the parabolic curve of equation y equals to x square plus 2 under the limits 0 to 3, and then we need to subtract the area under the straight line of equation x equals to y again under the limits 0 to 3. As we solve it, we have equation x square plus 2 dx in the limits 0 to 3 subtracted by x dx under the limits 0 to 3. Upon using integration, we get equation cube upon 3 plus 2x under the limits 0 to 3 minus x square upon 2 under the limits 0 to 3. Upon applying the limits, we get 9 plus 6 minus 9 by 2, which can be finally solved to get the area 21 upon 2 square units. This is the area of the bounded region of this graph.